Okay, so let's go through the solution to problem 11 on the practice test. Let's go ahead and read the problem. A 4.4 kilogram mass is suspended by two ropes from the ceiling of an elevator. Each rope is measured to be hanging at an angle of 39 degrees with respect to the ceiling of the elevator. The elevator is moving upwards in the plus y direction and accelerating with acceleration equal to 3.5 meters per second squared j hat. Find the tension in each rope. Find T1, the force of rope 1 on the mass, and T2, the force of rope 2 on the mass. Alright, so we have two ropes hanging up this mass in an elevator. We want to find the tension in these ropes. So tension we know is a force, and so we know we have to use force concepts for this problem. We have a couple of knowns which we can write down to begin with. We know the mass is equal to 4.4 kilograms, and we know this angle defined to be the angle of the rope with respect to the ceiling of the elevator is equal to 39 degrees. And we know the acceleration is equal to 3.5 meters per second squared j hat, which is telling us that the acceleration is only in the y direction. We have a y component of the acceleration equal to 3.5 meters per second squared. Okay, so it's good to write down our knowns, make sure we understand that. And our unknowns are T1 and T2. Right? We don't know the tension in these cables. This is a force problem, so we can follow our force problem-solving procedure, and the first step is always going to be drawing a free body diagram. To do that, I'm going to first define a coordinate system. Again, because forces are vectors, we need to know what is plus x, what is plus y. So I'm going to define the horizontal direction to be plus x, and I'll define straight up to be the plus y direction. And they actually define that for us in the problem. They define straight up to be plus y. To draw a free body diagram, I'll draw a dot to represent the mass, and I'll draw all the forces acting on that mass. Right? So the mass has gravity affecting it. The force of gravity, or weight, will be straight down. So that's our weight. And then there's two forces with components in the vertical direction. We've got T1, which is off to some angle like this. And we've got T2, which is off to some angle like that. Okay, so we've got three forces acting on this mass. That's going to be helpful for us. We have our free body diagram. We can see that it's the y component of tension 1 and tension 2 that is holding up this mass, and that's going to be accelerating this mass upwards, right, as this elevator accelerates upwards. Let's go ahead and follow our next step, which is always going to be expressing any force vectors which are not pointed along the x or y axis in terms of components. Right, so I can see that T1 is going to have an x component in the minus x direction. It's going to have a y component in the plus y direction. Likewise, we can see that T2x is going to have an x component in the plus x direction. T2x. And it's going to have a y component in the plus y direction. And once I do that, I can draw this little twiddle across both T1 and T2, which tells me that I've expressed these two force vectors in terms of components, and I don't really have to worry about those angled force vectors anymore. I can just solve this problem using the components. Now that I've defined the components graphically, we should try to figure out what they actually are numerically. And again, we don't know T1 and T2, but we do know the angle, so we can try to express these in terms of the angles. And we'll note that in the problem, they told us an angle with respect to the ceiling. So they told us this angle is 39 degrees. That doesn't really correspond to one of the angles in our diagram, right? We defined our diagram based on this location. But I can kind of see here that if I draw kind of a parallel line to the ceiling, that it must be the case, since this line is bisecting these two parallel lines, it must be the case that this angle is also 39 degrees. So I can recognize this is 39 and this is 39. Once I know that, I can figure out what T1x and T1y are. T1x is equal to T1 cosine of 39, because that is adjacent to that 39 degree angle. With T1y, which is this, or equivalently this, is opposite that 39 degree angle, so I have to use sine. So this becomes T1 sine of 39 degrees. Okay. Same thing for T2. T2x is adjacent to that 39 degree angle, so we have T2 cosine of 39 degrees, and T2y, which is this or this, is equal to T2 sine of 39, because again, that's opposite that 39-degree angle. Okay, so we've done a lot of setup here. This is always the setup you should do when solving any fourth problem. Now we can try to solve, and the step is always to go from our free body diagram to figure out how to apply Newton's laws, all right? And so we can see that in the x direction, we're not going to have any acceleration, so it must be the case that the net force on this mass in the x direction is equal to 0, right? So we can use Newton's first law in the x direction. So let's do that. The sum of the forces acting on the mass in the x direction must add up to 0. All right, that's Newton's first law. We can write down what are the sum of the forces in x. Well, I have one force in the plus x direction. I can see that here is T2x in the plus x direction. So I have T2x, and then I have one force in the minus x direction, which is T1x. So I'm going to write that in here with a minus sign, minus T1x, because I can see that's pointing in the minus x direction. These two forces must add up to 0. These components must cancel, so we have no net force in the x direction and no acceleration in the x direction. I can now write these out in terms of these angles. T2x, we wrote already, is T2 cosine of 39 degrees. T1x is T1 cosine of 39 degrees. Set that equal to 0. I can see my cosine of 39 cancels, and Newton's first law basically tells me something that's relatively obvious, that T1 has to be equal to T2. Okay, but it's good to go ahead and prove that. You could maybe make a symmetry argument to argue that T1 and T2 have to be the same tension, but we've gone ahead and proved it now, and so we can use this equation, the T1 is equal to T2, in the future in solving this problem to get rid of some unknowns. Okay, now in the y direction, we need to recognize that this mass is accelerating upwards, right? The elevator is accelerating upwards, which means this mass must be accelerating upwards. So in the y direction, we have to use F equals ma. We have acceleration. It must be the case that T1y plus T2y be bigger than the weight in order that we have a net force in the y direction and this mass accelerates upwards. So let's write that down. We know that the sum of the forces in y is not equal to 0. It has to be equal to mass times acceleration. Now that we know that, we can fill in what is the sum of the forces in the y direction. I can look directly at my free body diagram and see that I have T1y pointing in the plus y direction, and I have T2y pointing in the plus y direction, and then I have one force in the minus y direction, which is the weight. So I'll write that in as minus the weight. It's in the minus y direction. And the sum of these three forces must equal the mass times acceleration. Okay. Now we can go ahead and try to solve. I can write out that T1y is equal to T1 sine of 39 degrees. I can write that T2y is equal to T2 sine of 39 degrees. I can rewrite weight as equal to m times g, because that's my weight formula. And the sum of all of these must be equal to the mass times acceleration. Okay. I can now use the formula I derived already, T1 is equal to T2, to just go ahead and rewrite T2. Oops, that was really big. Go ahead and write T2 as T1. Okay. Those forces must be the same, so I can replace T2 with T1. And now I can see that this becomes 2T1 sine of 39 degrees. And I'll just move over the mg to the other side, m times g plus a. And so finally, I can solve for one of my unknowns, which is the tension in cable 1. Right, this tells me that T1 is equal to m times g plus a all over 2 times sine of 39 degrees. Okay, and we know g is 9.81 meters per second squared. We know the acceleration, that's something they told us in the problem, is 3.5, positive 3.5, so we can plug that in. And the denominator we know, so we can go ahead and plug in and find tension in cable 1 is equal to 46 newtons. Right? And therefore also tension 2 must be equal to 46 newtons. Alright, so we've solved the problem. We can recognize that we have this nice formula where the tension is actually going to be bigger than it was if the elevator was at rest. Right? Because we have positive acceleration, the tension in that cable has to be bigger because it has to apply this net force in the plus y direction so that the mass can have acceleration in the plus y direction. Okay, so that's a really nice problem. Let me know if you have any questions.